We talked before about how threads, when interacting with shared data or shared resources, can overlap and interact in ways that cause problems. And we talked about how locking is one way to handle those sorts of problems, and that it comes with some of its own possible issues like deadlocks and live locks. We'll talk about another way to approach these kinds of issues, and that is synchronization, in particular with blocking operations that are available in Java through several different methods. So what we do when we block is that thread execution is suspended until the program state is suitable for it to resume, and that may vary based on different conditions. Even using locks is sort of like this because it suspends until the program state of the lock being free is suitable for it to resume. These methods will provide us some other possible options for those two. So we call these blocking methods. The stack and the program counter of that particular thread are saved. So all of the variables and things that were available will be restored when the thread resumes, and it will resume at the place that it was previously executing. And some of the blocking operations that we'll use are the wait method, which is called from an object, it's worth noting, not from a thread necessarily. The execution will be suspended until that thread is notified somehow. We'll look at how things can be notified in a moment. Thread.join, so this is called from a specific thread. The execution is presumably suspended until another specific thread terminates, and we'll see some conditions where it's not necessarily suspended, but presumably suspended until another specified thread terminates. So we will sort of stop the current thread that we're doing until another thread is finished and is ready to join back. Some I/O operations are blocking operations. And so the execution may be suspended until the data can be read or written. And then there's thread.sleep, where execution is suspended for a given amount of time. And you should not use this for the kinds of synchronization that we will typically want to do. People often go to it because it's somewhat better known and it allows you to specify time, and that feels comfortable. And it's actually not a very good way to try to synchronize a program by getting it to, say, sleep for 10 milliseconds and then come back and then sleep for 10 milliseconds again and come back. This is bad behavior typically because it's wasting computational power, sleeping and coming back. We should be able to see conditions that we know we want to have true before the thread comes back. Synchronization is not doing busy waiting, like a loop that says, while something is false, just keep looping forever and then come out of that loop. That, again, is wasting computational resources. It's not synchronization. And again, no calls to thread.sleep. It's bad practice. It may sometimes get the job done, but it is bad practice and wastes resources. So join. Join suspends the execution of the calling thread. It is worth noting what calling thread means. Your program is executing inside of some thread. Even a single-threaded program has that one thread that it's executing inside of. The thread that's executing that calls to t.join is the one that will get paused. Thread T will not get paused. That would not make sense because we are waiting on thread T to finish its work until we resume our work. So if the main thread of my program calls t.join on some thread object that it's generated, then the main thread of my program will sit and wait. This is the kind of thing you may do where that thread is responsible for writing your results out to a file, and you don't want the user to change those results in the meantime while you're trying to write them out to a file, and you want to just sort of pause the program and have it wait until that thread is done with its job, that kind of thing. It is not pausing thread T, the one that's before the dot. It's pausing the thread that is active when join is called. If thread T has already terminated, then we don't pause execution of our thread. This call does nothing. It is available with a timeout of some amount, so that if the thread T gets kind of hung up on something or takes too long, we can come back and start executing again this calling thread, the one that was going on when we called join. So thread.sleep, you'll notice, is a static method. You call it from within an executing thread. So again, if I'm executing my main thread of my program and I just wanted the program to pause for a bit, then I could call to thread.sleep. People often jump to thread.sleep as the solution to all their problems because you don't need an instance of thread to call it. It's static. You can just call it from within the sort of structure of the program using the thread class, and it will pause whatever thread is executing right now. Even if you call from a thread object like T, it won't suspend T. It will suspend the calling thread unless T is also your calling thread. So it's useful for some things. If your program just actually needs to pause for some amount of time, then it can be useful. But it is not the solution to most of your problems with synchronizing programs. A thread can wait for a condition to be established by other threads. So you can call things like o.wait. You'll notice O here can be any kind of object because, again, it suspends the calling thread. So a thread can notify another thread that a condition has been established by calling notify with that same object. So o.notify will wake some thread that's waiting on O. So if you called o.wait and you call o.notify, then one of the threads who has called o.wait will get woke up and restored by a call to o.notify. And all of the threads could be awakened by calling to o.notify all. That does not necessarily mean that they all will get a lock or anything, because we're not talking about locking here. This is just notifying that something is, ready or that kind of thing. So if you were modifying a data structure, you want some of them to wait and one of them to get to modify it, and then that one can notify one thread or it can notify everybody that conditions are okay now. Establishing a network connection, you could tell everybody to wait on that network connection until it's established, and then you could notify everybody that that network connection has been successfully established. These kinds of things could be done. So these two methods, notify and notify all, do not notify all waiting threads everywhere. They notify threads that are waiting on the particular object that it's been called with. So it won't affect threads that are waiting on other objects. T.wait, again, will not suspend the thread T. It will cause the current calling thread to wait until someone notifies using the thread object T. So this is often wrong behavior to do T.wait like that. Typically you want it on some resource. Similar to our locks, but not quite the same. It's a notification system rather than a locking system. It's available also with a timeout so that you can tell it how long to wait, and then maybe it gives up and says, sorry, network connection timed out, or something like that. It is like locks in that there is no guarantee to be first in, first out, or fair when you notify just one thread. It may not notify the thread that's been waiting the longest. It may just pick a thread and notify it. You can combine this kind of method-based synchronization and locks. For example, wait does just this, because wait has to be called from within a synchronized block. So here we have a synchronized method. Remember that synchronized methods are synchronized on the object this. So whatever this is at the moment, that's what you're synchronizing on. And therefore, when we call wait there, it's the same as this dot wait, because remember, this dot is always implied in Java if you didn't specify another object beforehand. And so what's happening here is this method is synchronized on this, the current object, and we're doing some while loop. And if we find that there's not a need to hold on to that lock and we could pause our execution for a moment, then we can call to wait. Wait releases the lock and suspends the thread in one step. These can be considered instantaneous. Another word for instantaneous is atomic in terms of programming. This means it can't be partway done. For instance, our example with an array list breaking because its size got changed before the array got resized, that's non-atomic. We're saying here the lock is let go and the thread is suspended both immediately. You can't have one and oops, I didn't quite get to the other. So when a thread is notified, it has to reacquire the object's lock to continue inside of the synchronized block. So even if notify was called on this, then our wait would still need to reacquire the lock to continue in that synchronized block, which means if multiple things are waiting and they all get notified, they may still have to wait and pause longer to get the object's lock from, in the sort of waiting line of threads hoping to get that lock and continue doing their work. In most cases, using an if instead of a while is incorrect there because you might need to kind of come back and try waiting again or things like that. It's worth noting I give these references to the Effective Java book, and if you want more detail on why and if would probably be incorrect versus a while here, the Effective Java book in number 69 gets a little further into that. A call to wait or notify all by a thread that doesn't own the lock of O will throw an illegal monitor state exception. So you have to hold the lock to be able to call wait. You have to hold the lock on O to be able to call O.wait, and similarly for O.notify or notify all. A little bit more of an abrupt way to undo blocking versus, say, like the notify that sort of hands over the lock potentially and lets waiting threads get access to a synchronized portion of code. A little more abrupt way is the interrupt method. So if T is suspended, the thread T is suspended on a wait, a sleep, or a join, it will simply resume execution with an interrupted exception. So we may need to catch those exceptions, and you may have seen these in various places before. If T is suspended on an I/O operation, then execution will resume with a closed by interruption exception, meaning that I/O operation was sort of closed off or stopped by the interrupt call, and T is marked as interrupted. If T is already running and not waiting, sleeping, or joining, then it's simply marked as interrupted. If a thread is already marked as interrupted and it calls to wait, sleep, or join, then it throws an interrupted exception and keeps going if that interrupted exception is handled properly. An interrupted exception probably is handled in some way because it is a checked exception, meaning that it has to be caught. Here is an example where we call to sleep. If you tried compiling a line that just says thread.sleep, then for 3 seconds, then the compiler would get very angry at you because you are supposed to handle a possible interrupted exception. Even if nowhere else in your code do you call to interrupt, there are other things that can interrupt a thread too in an operating system, and so you have to catch that exception. You can't predict that it's not going to happen to you. There exist some very hard-line methods for terminating threads. You can call to stop, suspend, or destroy to forcibly stop a thread, suspend its execution, or destroy it entirely. And these are almost always bad. They will cause your program to be very ungraceful in many different ways. If you stop a thread while it's holding on to certain resources or things like that, it can cause problems. Similarly, for forcibly suspending or destroying it, the better solution is to just make a way that the thread can gracefully reach the end of the run method. This will allow you to do things like close out file handles that you might have open, let go of resources and locks and things, and really make sure that the program or that the thread ends its running cleanly. And so if you don't have any blocking operations, if you're not calling to sleep, wait, etc., then you can just have some Boolean that indicates whether your thread should continue running. And you can do sort of a while my thread is running, do whatever the work of my thread is. And you can write your own sort of gentler ways to quit the thread, like a terminate method that sets your running Boolean to false. That would cause your loop to exit, and maybe down here you could put any code that was needed to close out files or the other sorts of things you might want to do to clean up. So that's a smoother way to do this without blocking operations. And there are a couple of ways that we can do it with blocking operations. We have the try catch for an interrupted exception to allow our terminate to interrupt our thread if it's waiting on things or stuff like that. And we also could, in fact, do away with the Boolean for whether it's running and simply use the interruption to cause it to quit. Because remember, if we call interrupt on a running thread, it will mark it as being interrupted anyway, so we don't need the extra Boolean. We can use the interrupted state for whether or not our thread should quit its work. And just while we're here looking at some of the pieces of threads, there are a few other interesting thread methods that we might want to use from time to time. Thread.currentThread will give us whichever thread is running right now when the call was made. So that's one way to get access to whichever thread we're currently executing in. Set name and get name, these can be useful for debugging our program and seeing which thread is having problems or which thread is doing the work that we're seeing or things like that. Set daemon, it makes the thread a daemon, which essentially makes it so that it doesn't prevent the Java virtual machine from terminating. This can allow our programs to close a little more cleanly or things like that. Thread.yield makes the calling thread give up the CPU temporarily. Again, this can be useful for debugging to make sure that a thread kind of lets go for a minute and other threads can run, but probably not useful for an actual deployed program too often. IsAlive checks whether the thread is currently still alive, meaning that it has been started already and that it is still running and doing its work. But the main takeaways are that we've got these methods that allow us to do some synchronizing. We can give up a lock and wait for a while, give up the lock on a particular object and wait for a while. We can cause the calling thread to wait until another thread finishes its work and joins back with us. We will sometimes block on input and output, and we can cause some sort of temporary blocking by sleeping, but this is often not the best way to go. Often the letting go of locks or the waiting for another thread to finish entirely are a good way to go. And from time to time, if we really need to stop something that's ongoing in a somewhat graceful way, interrupting can be a useful way to do that and still be able to keep some of our synchronization and our good behavior between our threads. There is a Java util concurrent library that contains a lot of other things that can be very useful for more advanced threads and synchronization. It's got a wide range of possible applications for it. It helps enforce good design patterns for multi-threaded programs. It's probably pretty correct because it has a large user base and has been around now for a little while, though it's a newer portion of the Java libraries than some parts. It relies on some smart algorithms that are already implemented efficiently, probably in better ways than the average beginning thread programmer could do. It has options for thread pools, where you're able to get groups of threads to sort of work well together, and be able to submit particular tasks to them, cancel those tasks, and monitor how the behavior of getting those tasks done is working. It has implementations for concurrent data structures that are thread safe, and unlike the array list example before, they will have atomic operations in them. If you go to add something to it, it will get done in a way that's guaranteed not to be interrupted or mixed in bad ways. It has good tools for synchronizing, which you may have seen in other classes, like if you've done threading in C, for example. Queues, latches, barriers, semaphores. So some better ways for locking than those sort of simple built-in Java locking methods. This library provides some of those. It offers atomic variables of various types so that we can guarantee that the math that we do with two integers is actually going to be atomic. It's going to get fully completed in a single step that won't be interrupted by another thread. And it offers explicit locks with operations that are not supported by our synchronized blocks. If we want to get good ordering, if we want to get good guarantees of how our synchronization works, then the concurrent library can be a good way to do that. If you want to learn more about this level of concurrent programming and multi-threaded and multi-process sort of stuff, CS 735 is a great angle to go for that kind of stuff too.